chapter 19, the ideal gas law, the pressure of a gas times volume of a gas is the number of moles of the gas times the gas constant times T, or the number of particles in the gas times Boltzmann's constant times temperature. This is one of the fundamental equations in physics and chemistry that govern ideal gases, right? In this chapter, we introduced the ideal gas law. We don't go too much detail into it, but in chapter 20 and 21 and 22, when we go further into thermodynamics, we will constantly be using it a lot, right? So let's mention the units of this thing. Pressure is in units of pascals, or you can also use units of atmospheres. So that would be the units for the pressure, right? The units for the volume, if you use pascals, you want to be using meters cubed, or you could be using, if you're going to be using atmospheres, you could be using liters, right, for the volume. Right? And then N, of course, is the number of moles. R is the gas constant. So the gas constant is going to have two units. If you use the pascals and the meter cubed, you use 8.31 joule per mole Kelvin. Right? That's the, if you're using this and this, they go with that. Right? Or if you're using the atmospheres and the liters, you use 0.0821 liter times atmosphere over mole Kelvin. Right? 0.0821. Usually this is more often used in chemistry, the liter atmosphere mole Kelvin unit, and then this is used more often in physics, right? 8.31 joule per mole Kelvin. And then N, the big N, is the number of particles in the gas, which is equal to what? It's going to be equal to the number of moles times the Avogadro's number, right? Because Avogadro's number tells you how many particles there are in each mole of the gas, right? If we multiply that by the number of moles, we get the number of particles. So what is Avogadro's number? It's equal to 6.02 times 10 to the 23 molecules per mole, right? So then if we're multiplying that by moles, the moles cancels, and then you get the number of molecules or the number of particles, right? So that's the Avogadro's number, big N. Now what do we see from here? We see that there's also another constant, K. K is called Boltzmann's constant. It's used quite a bit in thermodynamics, especially when we get to the chapter where we talk about the speed of gases in a molecular distribution of gases in a container, right? So, and also the kinetic energy of gases. So the Boltzmann's constant is going to be equal to 1.38 times 10 to the minus 23 joules per Kelvin, right? Now you can see from this equation that since this is T and this is T, NR must equal NK. NR must equal NK, right? Well, does that make sense from what we have said so far? Well, we have here NR, and then big N is equal to what? It's equal to the number of moles times Avogadro's constant, right? N times Na, right, times K. So then what happens? The number of moles N cancels the number of moles N, so we get the gas constant, R, is essentially just equal to Avogadro's number times Boltzmann's constant. So they're just all interrelated, right? Na times K. So let's see what we get. If we multiply Avogadro's number, 6.02 times 10 to the 23, and what are the units of that? Right, the units of that was molecules per mole, right, times Boltzmann's constant, which is 1.38. 1.38 times 10 to the minus 23 joules per Kelvin, right? The 10 to the minus 23 and the 10 to the 23 are going to cancel each other, right? And then you're going to get 6.02 times 1.38. Well, if we multiply that, 6.02 times 1.38, we get the gas constant 8.31, right? R is equal to 8.31. What are the units of that? So it will just be joule per mole times Kelvin, right? So that's the units of the gas constant that I gave you earlier, and then the 8.31 is the same number that I gave you earlier. So you can really see here that the product of Boltzmann's constant and Avogadro's number is essentially just the gas constant, right? The other thing that we can mention about the ideal gas law is that it gives us a relationship between the pressure, volume, and the temperature of a gas. So if the number of moles of the gas are not changing or the number of particles aren't changing, we can say PV is proportional to the temperature, right? If the moles aren't changing, so then what's going to happen? PV over T is equal to PV over T. So it's going to be P1 V1 over T1, P2 V2 over T2, right? So this gives us a relationship between pressure, volume, and temperature that they all must obey, and then it must be a constant, right? So we can do a quick example within the theory section here. If we have a container of gas, right, and it's a cylinder right here, if the initial temperature is equal to, remember for this equation, as I mentioned earlier, since the equation relies on temperature, the temperature must be in Kelvin, right? You cannot use Celsius. So we're always going to be using Kelvin here because it does not rely on the change in temperature. So the initial temperature, let's say, is equal to 300 Kelvin, right? So let's say I press on the cylinder, right, and it goes down, and final volume, so let's say the initial volume is 10 meter cubed, right? And then the final volume is going to be equal to 2 meter cubed. So let's say it goes down. Right, so what's going to happen here? Well, of course, the pressure and the temperature is likely to change, right? The initial temperature is going to be here 300 Kelvin. The initial volume is 10 meter cubed. The final volume is 2 meter cubed. And then we don't know what the initial pressure is or what the final pressure and the temperature, right? But the problem can tell us some information about that. Is this process being done isothermally? Is it being done isobarically, or what's happening? But in general, what will happen though, in most general circumstances, the pressure of the gas will rise and the temperature of the gas will rise, right? So it will look something like this. P1, and then the 10 cancels the 300, so you get here 30, and then you have P2 times 2 over T2, right? So in the general situation, the pressure of the gas is probably going to increase. Let's say 1.5 times, maybe 2 times, right? Because the gas is forced to occupy a smaller volume, right? So let's just say the pressure of the gas increases 1.5 times. So P2 is equal to 1.5 P1, 1.5 times the initial pressure. So then we can find out what the final temperature of the gas is, right? So we can say here P1 over 30 is equal to P2 is equal to 1.5 P1, right, times 2 over T2. And then, of course, the P1 cancel, and then T2 is going to equal 30 times 2 times 1.5 is 3, 900 Kelvin. So the final temperature is 900 Kelvin. So it went from 300 Kelvin to 900 Kelvin, the temperature tripled, right? What if the pressure somehow we kept it the same? We managed to keep the pressure the same. That would be an isobaric process, right? Constant pressure. Then what would happen? Well, then this number here would be equal to P1 over 30, and then this would be just P1 times 2 over T2, right? The P1 cancel, T2 would equal 600 Kelvin. Right? So if we manage to keep the pressure constant, the temperature will not rise as much, right? That makes sense. Let's analyze this a little bit more in detail to see why that makes sense. We have P1 V1 over T1 is equal to P2 V2 over T2, right? We said it was equal to 10 meter cubed, and V2 was equal to 2 meter cubed, so it's equal to 1/5 of V1, right? So we have P1 V1 over T1, P2, and then this is equal to 1/5 of V1 over T2. Then the V1 and the V1 cancel, equal to P2 over 5 T2, right? Now, if the pressure goes up, let's say 1.5 times, 2 times, 3 times, if this goes up, this T2 has to go up to compensate for that, right? The T2 has to go up more. If it stays the same, let's say, then the T2 does not rise as much, right? The more the pressure rises, the more the temperature rises. But in reality, what is actually happening is the opposite, the logical reality. If the temperature is rising more, that means the molecules are moving faster, and therefore that's why the pressure is more, right? So it's not that the pressure is dictating the temperature, but more the temperature is dictating the pressure. So if the temperature went from 300 Kelvin to 900 Kelvin, that means the temperature tripled. The molecules are now moving much faster, and the pressure is going to be higher. It's going to be 1.5 times the initial pressure, right? If the temperature only goes from 300 Kelvin to 600 Kelvin, the temperature only doubles. So then the pressure doesn't increase at all. The pressure stays the same. So it's actually the temperature that is dictating what is happening to the pressure, okay? So you can see from this example, you can play around with numbers, try to make sense of the ideal gas law and see what the meaning of the ideal gas law is, right? So next I'll show you some examples of the application of the ideal gas law. We won't go too much into detail in this chapter, but in chapter 20, 21, and 22 we'll go a lot more detail. Thank you very much.